record will start right now.
Okay, I will start my presentation. And I'm not sure how to... Are you seeing my screen?
Yes, we can.
Okay, are you now seeing my presentation?
Yeah.
Okay, great.
I think you can see your presentation and how in the same time, and us in the same time, but we can see your presentation definitely.
I actually cannot see... Wait, it's weird. Sharing your entire screen or browser can...
No, yes, I think on Google Meet you can only share your screen, but when you do that, you can see any more the participants.
All right. Okay, so now you see my presentation. Yes. And I don't see you.
Yes.
Okay, great. Well, please feel free to interrupt me. Or it's gonna be interesting to not see anyone. So feel free to interrupt me if there is any questions that you have, anything that feels unclear, or even just you're curious about. I would love this to be more of an interactive presentation rather than something more formal and passive. So I may also ask you some questions in between so that I make sure you're doing okay. All right, so here is an introduction to exoplanets and ocean worlds, and I will describe later what that means. First, let me describe the plan. I will first introduce myself. I will then dive into the exoplanets description. I will give an introduction to exoplanets. I will describe some detection methods, and then I will describe why are atmospheres of exoplanets so important. I will then describe the core of this presentation, which is the ocean worlds, and how that fits into the quest for extraterrestrial life, and give an introduction to astrobiology. All right, I just finished my PhD like exactly a month ago in astronomy and astrophysics between several cities. Well, my main university is based in Paris, but I was for most of it based in Hawaii at the Subaru Telescope, which is an 8-meter of diameter infrared telescope. And I was there for about 3 years, and I am also related to the University College London for more work on exoplanet atmospheres. And I have 2 masters, one in engineering in optics and photonics, and one in fundamental physics from Imperial College. And I have several internships in astronomy and space. Oh, by the way, my undergrad was in fundamental physics, and I had several internships in different institutions. And I just would like to share with you how I actually was not always a good student. I had some really hard times, starting in high school. Actually, sometimes I was like even the last of the class of my classmates, and had really bad grades in mathematics and physics. And I was continuously basically going back and forth between good grades and bad grades, and I was continuously in lack of self-confidence of what will I be able to do, and if there is something that really saved me and had me get to the PhD level and had amazing internships with amazing people, it really is my passion for astronomy. And so I just would, because now you are in 3rd or 4th year of university, and I feel how sometimes it can be stressful to be in situations where you just have lack of self-confidence. Have you guys experienced something like that?
Yes, we have experienced something like that. It's very sad and tiring.
Yeah. But at the end of the day, grades don't matter that much, and this is where I'm here to tell you that there is a future in doing cool things, even if you don't do so well at school. And contacting the people and showing your interest, it really is what matters the most. And by the way, I think I showed my email at the beginning, but I'm not. Yes, so here is my email. And if ever at any point you want to contact me for any questions that you may have, feel free to do so. All right. So what are exoplanets? Exoplanets are planets that rotate around other stars than the sun. And they're especially interesting because they are just far more diverse than the planets that we have in our solar system. Yes, that's a video that shows the planets discovered by the Kepler mission. And you see that those are discovered in transit spectroscopy, meaning that they are pretty far away from most of them, and they are much smaller than the solar system. And here it is pretty much to scale. And there has been now over 5,200 planets that have been discovered that are just far different than the ones in our solar system. So there is a lot of interesting things to discover. And you see here, I don't know if you see my mouse, but on the right-hand side, how some planets are just extremely close to their star, and there is an interesting dynamic happening. Or even here, it's like sometimes just very, very weird and very interesting things when the solar system is just simply the planets that we know of. In some other cases, there is a very just weird, harmonious dynamic. And so here are some images, some of real exoplanets that have been detected in what we call direct imaging. And I will dive more into the different description as well. But here is on the right-hand side, here is something that we call the beta pictory system. And so we have seen over the years the planet rotating around the star, changing orbit. On the left-hand side here is the system that has 4 different planets. And you see here observations at different times showing the orbital motion of the planets. And so the beta pictory system, it's something that I actually focus on during my my PhD. I just published a paper, actually, that was this week published. And this system is really cool because it describes how planets form. And so here is an artist impression. So you have at the center of it, you have the star, and then you have a big giant disk of gas and dust. And the planets, basically, they accrete mass along their way, and that's how the planets form. And this system is also very interesting because you see there's comets here in the artist impression, and we see there's comets falling into the star. There is very interesting structures that we see in the disk, and so planet formation is also very important, is crucial for understanding just the exoplanet diversity, where they come from, and that also gives insight in how our own solar system, how our own Earth was formed. Because by looking at how other systems form, that gives indications on how our own planets form. All right, so far so good.
Yes, ma'am. So far so good.
Okay, sorry. Say that again.
So far so good.
Great. Okay. Okay, so another introduction to something that I've been working on in my PhD, which is called adaptive optics. And it's something that is necessary to have for observing exoplanets from the ground, from Earth. And here is an example of the Subaru Telescope on the right in Hawaii. And so basically the main point is to correct for the Earth's atmosphere. The problem is when we observe from the ground, we have to take the light coming from the stars that goes through the Earth's atmosphere. But the Earth's atmosphere is something that has an impact on the shape of the wave, on the light, what we call the wavefront, because the light, as you know, is a wave. And so when it goes through the Earth's atmosphere, it's not a flat wavefront, but it's something that is shaky. And this is scientifically, we cannot really study it. So that's why we need adaptive optics that, in a nutshell, compensates for the Earth's atmosphere And as you see here on the right-hand side, I cannot find my mouse. Anyway, you see here on the right-hand side, there is basically three main elements. There is what we call a wavefront sensor. It's something that will understand that will sense the shape of the wavefront. And then it will send information to a wavefront corrector, which is a deformable mirror, which will take the exact opposite shape of the incoming wavefront to send it flat back to the scientific instrument. And this is done through a feedback loop. So basically, it's like kind of automatization, control loop, if ever you have done some control theory. And it's what we call a real-time control, because the atmosphere is continuously changing. So we need to correct in real time for the Earth's atmosphere. All right, and there's several big telescopes that use adaptive optics. In fact, all the telescopes that are observing in the optical and in the infrared need to use adaptive optics. So it's really something that is very present in all fields of infrared and optical astronomy. And here is the arrows. It's the telescopes that I've been working on. On the right is the Subaru Telescope in Hawaii. In the middle is the 30-meter telescope that is not built yet, and the extremely large telescope, which is a 39-meter diameter telescope that will be based in Chile. And is the first light is supposed to be in 2028, I think. All right. Here's just to show on scale how huge the extremely large telescope will be. It's going to be a big revolution, actually, in the fields of in many fields of astronomy, and especially exoplanets, because we will be able to detect in direct imaging planets that are, because right now in direct imaging, in exoplanets direct imaging, we cannot really detect planets that are like Earth. We detect planets that are much bigger, like Jupiter, like further away. And with this instrument, we will be able to detect Earth-like planets around Sun-like stars. So here is just a maybe you don't need this, but it's always cool to have an idea of the dimension of the universe. This is just in terms of light days. So we're still in the solar system, and the closest star from us is 4 light years away, 4.2 light years away. It's the Alpha Centauri system, which is actually a triple star. So it's like 2 very close stars rotating to each other, and then there's another star a bit further away that gravitates a bit away. So yeah, that's the local area where we have so many stars, and we're taking a step back in our galaxy. And so now when we study exoplanets, direct imaging, we look at the ones that are very close from us, within maybe 100 light years. In transit spectroscopy, we can look far further away. And mainly in exoplanets, we really just focus on the Milky Way galaxy. And in still our local environment. Well, and then that's still something to scale what other galaxies. But imagine, so there, I will discuss that later as well. But there is more planets than there are stars, and you see here there's like millions and even trillions of galaxies, and each of them have about 200 million stars. Sorry, 200 billion stars. And imagine how many planets that means we have. It means we really have a huge amount of planets, and the probability of having life that is extremely high. All right. That's the, basically the big structure of the universe. It's we call the cosmic web. It's just a lot of galaxies, meaning a lot of possibilities for exoplanets. And the sample that we have around us in our Milky Way galaxy is tiny compared to what there is in the universe. All right.
Whoa, this is crazy. No.
Right? Yeah. Yeah.
Sometimes when you put the video, sometimes your voice, we can't really heard it, but we still have the video, so it's fine. But when you talk in the same time that the video, sometimes we can hear you well. Just
okay. Good to know. Okay. Other than that, so far so good. I'm curious if you knew about adaptive optics before. Have you heard about adaptive optics? What I just described here?
No, I had no idea. I don't know about Mrs. Tandiwe or Miss Tandiwe or others.
Yeah, it's something we usually don't learn until way later because it's very specific to this field of astronomy. May I ask, what are you studying?
I'm studying mathematics and physics.
Great. Okay, cool. Okay, was it clear enough how I or should I step up or down? Is it clear so far?
It's okay.
Okay. Okay. Well, feel free to let me know if you have any questions.
Okay.
Oops. There we go. All right. Yeah, exoplanets. So actually, the first exoplanet was detected in 1995, in October 1995, in south of France. It's actually where I discovered astronomy. And it received a Nobel Prize. Those who discovered the first exoplanet, so Didier Queloz and Michel Mayor, here on the right, they're the ones who received the Nobel Prize in 2019 for the first exoplanet discovery. And Didier Queloz, back then, he was still a PhD student. And yeah, like 25 years later, they received a Nobel Prize. I remember that was at the very beginning of my PhD, like I think the first week or second week of my PhD. And so after that, exoplanets became very, very popular. And just everybody wanted to know about them and ask me about, to give presentations like what are exoplanets and how come did it receive such an interest and what does it mean for humanity as well? All right. So why? Oh yeah, sorry, that's what I meant. So here is the artist impression of the first exoplanet that was discovered, which is its name is 51 Pegasi b, and it's a very weird planet, and because it's like a Jupiter-like planet, but that is extremely close to its host star. It's like rotating around the star, orbiting around the star between about 5 days. And so it's like what we call a hot Jupiter. So it's extremely, extremely close and extremely hot. And hot Jupiters are actually the easiest planet to detect, mainly because they're just so big and so close. And so it's very easy. They have a gravitational pull on their star. It's very easy to study them.
Okay, no, you can see it, but Mosa, I have a question. She raised her hands.
Yeah.
Oh, yes. Has there been like any proof of life, even in our Jupiter? Has there been a proof of life there? And even in the exoplanets, has there been a proof of life?
So actually, not yet. And right now, and there is what we call the Fermi paradox, which I will discuss later. There's just so many exoplanets, but so far we haven't had any proof of life. We have tried to listen to radio wavelength and have radio telescopes to basically detect kind of like intelligent signals, but so far nothing. There is many exoplanets that are discovered, and we're just starting to be able to study their atmospheres, but also so far there is nothing. And the main reason for that is because, well, exoplanets are actually really far away, and so it requires quite some technological development to be able to observe them, to study them, and to possibly detect a trace of biosignature, what we call biosignature. So it's like a proof, like a signature of a bioactivity, of a life activity. And we're just at the beginning of being able to have the technology in this. And yeah, so far there has not been any life discovered. Statistically, it is pretty much impossible that there is no life outside Earth, but it is not enough to say for sure there is aliens. And actually, this was my next slide. Why do we study exoplanets? And so the first answer to that question is to first understand what is our place in the universe. How do we fit in? How is our planet? How does it compare to other planets in the universe? And is our case unique? Is there other things that are like us? And main question is, are we alone? Is there other ways to detect, is there ways that we may be one civilization among many others? And yeah, so far we are still trying to answer that question. Does that answer?
Yes, thank you.
Of course. By the way, I don't see when you raise your hands, so feel free to actually, maybe I should. What if I do that? No, it doesn't work. Yeah, feel free to just interrupt me.
Yes, guys, just pop up in the conversation, put your mic on, and there we go. Okay, so I'm still here, but I have another call, and I will be back, but I'm still here. Okay.
Okay. Okay, great. So I have a question for you now, and I will take a little break on the presentation so that I can have a look at you. How many Earth-like planets do you think there is in the galaxy?
Well, I've heard of one in high school. I just know one.
Okay.
Yeah, but I have no idea what it does, where it is located. I just heard someone say, "Oh, there's another planet that looks like Earth."
Okay. And do you want to give a guess at how many Earth-like planets there are in the galaxy?
I'm just gonna go with one.
Okay, just one planet, just one Earth-like planet. Not necessarily that was discovered, just like how many there would be.
Pardon?
I'm not asking how many have been detected, but just how many would there be?
Oh, I think a lot. I don't want to say infinite, but a lot.
Okay, that's an answer that I like. Yeah. Yeah, Rato, do you wanna give a guess? All right, maybe I will give the answer. So we stay on the Milky Way galaxy. Here is an image of the Andromeda galaxy. And the question is, how many Earth-like planets there is in our galaxy? So imagine there is the galaxy that has between 100 billion to 200 billion stars. And we know there is at least 4 times more planets than there are exoplanets. And so the question is, how many, because there is, like about between 400 to 800 billion exoplanets, because there is 4 times more planets than stars, then if we consider that there is only 10% of these planets that are Earth-like planets, which is, it's a very honest estimation to have 10% of planets that are Earth-like planets. Well, that still means there is approximately 6 billion Earth-like planets in our galaxy alone. Is that shocking to you?
So can we like move to those planets, or the atmosphere is just different, or the conditions that we live in here?
Yeah, no, unfortunately, we cannot move to these 2 other planets. They are way too far away, and we do not have the technology. They are like, the closest star is 4.2 light years away, meaning it takes 4 years for light to come and reach us. Yeah, light year is a unit of distance, of how far does light goes in 1 year, and because it's so far away, it would take, even if we go at 20% the speed of light, it would take 20 years to get there, to the closest one. And so all of the other ones are very far away. And so yeah, it's impossible, at least in our current state of civilization, to go there. All right. And so the Fermi paradox.
No, it's the. Do you think we will be able one day to go to?
It's hard to say, because like that would require quite a huge miracle, like a what we call a wormhole, which is a way to kind of go from one spot to the other without traveling. If we try to just travel in the normal way, we won't. At least I don't believe we will, because that would require quite some. There is some science fiction things, like movies that try to show that, and how much the lack of gravity during the travel would have such an impact on the body, and people would not survive, and there is a lot of things that are so challenging to overcome, that I don't actually think that will ever be possible. And that's one of the beautiful things of exoplanets as well, is because we see so many of them, but they are so far away and we are nowhere near to even be able to consider how we could get there. And that really shows how, well, we have nowhere else to go but to take care of our planet. We have no planet B, and our planet is small and fragile and precious and extraordinary, and we pretty much have to take care of it.
Powerful. Thank you.
Yeah. And so the Fermi paradox is where is everybody? There is Enrico Fermi was an Italian astrophysicist, and he was like, well, if there's so many stars, then there must be, back then there was no exoplanet detected, but he knew there would be very likely planets that would be detected at some point. And that would very likely, just the universe is just so big with so many stars, life should be abundant. So where is everybody? What's going on? Where are the aliens? And the paradox is really that there is so many ways that life should be really abundant, but we still haven't discovered anything. So what's going on? And there is many answers to that. Maybe you've heard about the I forgot the name right now, but this equation that just tells how many civilizations we can have. And here, one of the main answers is because it's just so far away. So it's we are really at the beginning of being able to study them and detect them. And maybe actually as well, life is not as abundant as we think it is. And maybe just intelligent life is not as abundant. And then that leads us back to this question: what do we consider as intelligence life? what is consciousness? What makes life intelligent? And so something that we're looking at in exoplanets is, to also study their atmospheres and detect if there is what we call a technosignature, like a proof of maybe a fancy molecule that would only be artificially made, or even just a bioactivity, like a simple, just like simple bacteria that emits methane, for example, that would be indicative of that. And it happens that actually exoplanets are far more diverse. Here is the example of what we call a lava world. So it's basically a planet where it's just only volcanic activities. Here, remember when I was mentioning the Alpha Centauri system, which is a triple star? Here's one of them. And here's interstellar with icy worlds, where it's like so cold, but there is water in an atmosphere. It's just pretty much just ice. And there is the hot Jupiters that are extremely close to their stars, like huge gaseous Jupiter-like planets that are rotating so close to their stars. And then there are ocean worlds. Here is interstellar again. And so, and there is red planets. So basically, actually the red stars, what we call M stars, they're by far the most common star in the galaxy. There is many planets around them. And so that makes worlds where it's basically all red. It's like continuous sunset all the time. And in fact, what we see in real life when we detect exoplanet now, we actually find that reality is far stranger than fiction. And well, maybe you know that science fiction has been quite popular, well, pretty much in the last half century, I would say. And people have tried to imagine things, and now with exoplanets, we actually see how what we discover is far stranger than what we can imagine. So it's we still have so much to discover, and it's very very interesting to see, what are the different things that we can look at, and how is that even, meaningful in understanding our place in it. All right. Now I will give an explanation of how do we detect exoplanets. And here's that maybe a little bit technical at times. So if ever I'm going too fast, feel free to stop me. I may take a little break in between to check with you how you're doing. So one method, indirect method, is called the transit method. So what we do is we look at the stars, the star brightness, and we wait for a planet to pass in front of it so that the brightness decreases a little bit, kind of like dims a little bit. And so by looking at the star brightness and looking at when it dims, we can detect exoplanets. And this is called the transit method, which is the method with which we detected the most planets. There's like 4,000 planets that were detected with this method. And it's still ongoing and ongoing so far. So it's a very powerful method. Here is the example of the TESS telescope that was launched in 2018. And that is basically looking at the whole sphere of the sky. Every month is spending time on one part of the sky and trying to detect exoplanets in our nearby environment. And another indirect method is to look at what we call the radial velocity. So here, as you see, as the planet gravitates around the star, it has an impact on its gravitational position, like the gravity has an impact on the position of the star. And so by looking at the spectra of the star and seeing how the rays just like shift, we can infer whether or not there is a planet around it. And I showed at the beginning another method, which is this time a direct method. It's simply called direct imaging. And this is why we need adaptive optics. Another big challenge beyond the Earth's atmosphere that we try to overcome is the fact that the star is actually far brighter than the planet itself. So we really need to find a way to we're completely blinded in some ways by the star itself. So we put what we call a coronagraph, which is just a mask in front of the star so that the planet's contrast can increase, and so that we can detect planets, because otherwise we would really struggle. Imagine, actually, let me describe you that. Imagine you are, I don't know if you can see me. Okay, imagine you are, so for, I usually give Hawaii and California, but maybe, okay, imagine you are in South Africa, and actually imagine you are in your country, in Lesotho, and you try to observe a planet. Well, you're trying to observe a firefly next to a lighthouse in Cairo, in Egypt. So it's like super far away, right? Imagine the Earth is flat, so there is no Earth's curvature. It's just like flat, and you're trying to observe this little tiny fireflies, like a butterfly, next to a very powerful lighthouse. So not only is like super far away, what you're trying to look at is extremely small, and that's why you need a huge telescope, like the one that I was describing. So that's, but also then the problem is also you have the lighthouse that is so bright, right? And so that's why you need to first put a mask in front of the lighthouse to then be able to see the firefly that is in Cairo from where you are in your country. Isn't it crazy? Is it clear so far? Am I going too fast?
Guys, are you still there? Mosa? Some people come and get off. I think they have a problem with the Wi-Fi, because they come and they get off and they come back.
Yeah, I see. How about we just wait until they come back, so that it's we just check, so that I just make sure that they are not missing.
But I think no, Mosa was there, and because she was not able to talk, she just get off, and she will probably
come back.
Yeah. Sometimes, like at the first time she connects, she had a problem with the microphone, so she disconnects and she come back.
Okay. What do you think so far? Is it appropriate level?
Oh yeah. For me, I'm able to understand, so
okay, good.
Appropriate level.
Okay, good.
This is amazing. I had no idea of all of this. It's whole new for me, and yeah, I'm just amazed about all the data we already have. But I mean, we don't talk about that at school, but I think we need to have like a little window of all this new data at school, just to know where we are,
Absolutely.
This is amazing. Yeah, when you was talking, I was thinking about my own class. I teach in a secondary school, and I was like, my students have no idea, even me, but if they know that, they will just go crazy about that.
Yeah, well, if you want me to come and talk to them,
yeah, it will be great. I have to organize something with you.
Well, I would absolutely love that. And which level are you teaching?
I'm teaching on les terminales, the sixth grade.
Nice.
But also I teach everybody. In Belgium, it's a bit special, so I teach everybody. I teach chemistry and biology.
Okay.
But I have the first grade, donc c'est la fin début du secondaire. Chez nous, c'est pas tout à fait comme chez vous. Mais donc, ils ont 12 ans, quoi. Et ceux-là, je les ai que en techno.
Ils ont 12 ans?
Bah oui, nous, les secondaires, ça commence à 12 ans jusqu'à 18, tu vois.
Alright.
Du coup, j'ai toute la gamme. Et je donne chimie et bio aux grands, et je donne techno aux petits.
Ah, trop bien. Nice.
Et il y avait justement un chapitre sur l'Odyssée de l'espace. Et tu vois, j'aurais adoré pouvoir leur to tell them all the things you're talking about, but I can't.
Well, if ever you want me to talk about it even remotely, I'm happy to do so.
Oh yeah, sure. Maybe we can organize something remotely.
Yeah.
Cool. So Mosa, you come back. You are here, the older Alfred. Welcome. I saw you came after, but feel welcome, and all the other that came after feel welcome. Is it okay for you? You can follow even you didn't heard the first part. Like Alfred and the others. Oh, at least Mosa, you are still there.
Yes, I'm still here, but the network is a bit unstable.
All right.
That's why. Okay. That's why maybe the others can talk. But do you think that they heard us?
Yes, I think so far just have to like find the right spot.
Okay.
But if they're still on the Zoom call, then they can hear everything.
Okay, cool.
Okay, great.
Yeah, because I see them come back again, so I think they heard, but they're not able to interact with us.
Okay.
So we will just go ahead.
Okay. Well, if ever you have any question at any time, you know what? Is there a texting thing in the chat? Yeah, okay. I'm sending on the chat my email address. So if ever there is something that you missed or you would like to discuss or even just, yeah, just talk, feel free to reach out and we can organize a call.
Mm.
All right.
Thank you, Nour.
So I mentioned the direct imaging method and how challenging it is to do that. So we don't really imagine as we see this little video that is very cute. But there is decades of hard work of hundreds of people to try to be able to do that. And it's a huge technological achievement. And actually, it is also thanks to exoplanet direct imaging that now you have on your phone, you have the cameras, because we needed to improve so well the detectors to be able to receive the photons from the exoplanets. That really made a huge step forward into sensors, into camera sensors, and following that, it became a lot easier to have small cameras on simple smartphones. I mean, simple. You see what I mean? So yeah, astronomy plays a huge role into many aspects of technology, even the internet, even medicine. There is another presentation that I often give is why do we study astronomy? What is the point of astronomy and space exploration, and what are the benefits of it in quantifiable benefits with concrete outcomes in technology and medicine and other fields? And what are the unquantifiable benefits? For example, you know how in the 1960s with the space race and going on the moon, there is so many children in America that got very inspired by it. And following that, there was a huge generation of just children that wanted to become engineers and scientists. And that created a huge boom in the American industry and economy. Because all of these kids were inspired by the space exploration. And there were some people who made some calculations for $1 single invested in the Apollo program, the space race program. There is over $20 that got returned due to the result of inspiration on the kids. So did you guys know that?
No, we had no idea. Well,
Yeah.
I didn't.
Yeah. Isn't it cool?
Well, also, I did not have any idea about that at all.
About what you said?
I was saying I did not have an idea about that at all, and it's also amazing.
Yeah, right. Yeah. Okay, I'm glad you like it. So I described how we need to block the light, and here's an example of a coronagraph on the sun. And when you block the light for the sun, you actually see a lot of like sun flares, we call that, and protuberances that you see here on the left. So here's that's an example, and imagine there is a little planet next to it. Maybe you've heard about the James Webb Space Telescope, which was launched in space in about a year now, in Christmas Day last year.
Yes, I know about that one.
Okay, great. Well, the James Webb Space Telescope is an incredible telescope that is now active and has just amazing results. And this telescope, here should be a little video of the description of its deployment in space. Now it's fully deployed and it's running well and it's all well. But it's a telescope that we all expected to have in space, because it's 6 meters of diameter, and so it's like the big brother of the Hubble Space Telescope, which maybe you've heard of. The Hubble Space Telescope is 2 meters, and this one is 6 meters, and it's basically a gem of technology. So as you see here, deployment video is a little bit long, but pretty much that's kind of like, oops. It's pretty much the idea. And the James Webb Space Telescope was designed to study exoplanets, especially. And there is a coronagraph, there is a spectrograph to look at the light of exoplanets at different wavelengths, and it's also designed to study very distant galaxies. So basically look at galaxies from which their light was emitted, like at the very, very early time of the universe, like 200 million years after the Big Bang. And so that's
I have a question. Is it the one responsible for the buzz that was created with people? There was news recently about the universe being a lot bigger than it actually is, and people were going crazy. Like, it's the end of the world. It's responsible for that.
Responsible to send such a telescope when the world is falling apart?
No, like, is it the one responsible for finding out that the universe is actually larger than we anticipated?
Do you mind sending your question in the chats, because you're cutting off a little bit?
Oh, okay.
Yes, guys, don't hesitate to just write your question. Even she's still talking. You can just drop your question in the message box, and we will be able to read it.
Okay. Dora, did you understand the question by any chance?
I can see that. I think she's writing that.
Okay. Okay. Well, I will keep going, and I will come back to your question in a couple of minutes, so we can move on the same page.
Yeah. Perfect.
All right. And so I mentioned the James Webb Space Telescope, and there is other space missions that are really just focused on exoplanet direct imaging. And here's an example of the HABEX proposed mission, and it's a pretty fancy telescope with a coronagraph, pretty much, that is in space, deployed in space, that is located then super far away, to be able to detect Earth-like planets around the very nearby stars. So basically, we really try to have a sample of the planets within 5 parsecs, which is a unit of distance, which is pretty much like 15 light years. And we try to understand within our close neighborhood, you know, within 15 light years away from here, to really try to study what are the exoplanets. That's not necessarily interesting. What are the exoplanets that would possibly have life? So the point is to try to find life in our nearby environments, and that's the main point. All right, so now that I introduced the different detection methods, mainly transit, radial velocity, and direct imaging, here is a graph showing how these detections are doing. And so here on the left, you see it's mainly green over the years. Sorry, I didn't update it. And the transit method is by far the one that is detecting the most planets. And then in red, there is the radial velocity. So at the beginning of exoplanet discoveries, it was mainly radial velocity. And so now, direct imaging, we start detecting more. There is another method which is called microlensing. It's basically using just like how light gets bent by gravity in certain ways to then be able to magnify the light of a planet and detect whether there is whether planets is here or not. And here on the right-hand side, it's a diagram of a mass period distribution. So basically the mass of the planet and the period, the orbital period of the planet. And so mainly it's, and the unit is Jupiter masses. So, and you see like the green clump at about 1 Jupiter mass. And most of the planets that have been detected are Jupiter-like planets, a lot of very big planets. And you see there's like a distribution that is not very homogeneous. And the reason for that is simply because we have observational biases. The detections that we, detection methods that we have do not necessarily allow us to have a very good sample of being able to see the diversity, because we're just at the beginning, so we're still feeling that understanding and that distribution. And that's actually one of the focus of the big focus actually of the exoplanet fields nowadays, is to really understand this diversity. We see we have biases, and there are things that we see and things that we don't see, but we know we should see. So that's the main question. What is it that, how do we fill the gaps that are here, and what is exactly the exoplanet diversity in terms of mass, in terms of distance as well? And that is also intrinsically linked with how planets form. All right, now I will focus on.
She dropped the question. So I think she's talking about the James Webb Telescope, and she asked, is this telescope responsible for the recent news that the universe is getting larger and larger than we thought?
I actually don't know which one you're talking about. I'm not even sure. Yeah, I don't know what you're exactly referring to when you say the recent news. There is over the last years, there has been a finer understanding of how is the universe expanding and at what speed is it expanding, and a lot of that is linked with the understanding of the Hubble constant and the constant of the universe, and how black matter is having, and black energy is having a role in the accelerating expansion of the universe. And so some of that is linked with particle physics, and some of that is linked with what we call the CMB observations. So the cosmic microwave background. So basically at the very beginning of the universe, we see basically a remnant. It's like kind of like a phantom in some ways of the very beginning of the universe. So that's one way to look at the universe expansion. And another way, and this is where the James Webb Space Telescope could have played a role, is by looking at very, very distant galaxies from the very, very early. time of the universe. And basically by looking at their distance, we can basically have an indication of basically how much faster the universe is expanding. So does it answer the question?
Yes, thank you.
Of course. But if ever you have some like a reference of a paper, just let me know. I'm usually more looking at the discoveries on exoplanets. So I don't always keep up with the big news, because news are coming all the time, right? It's like now it's like the telescope is taking data all the time, and it's coming very, very fast, and to keep up with everything is quite a challenge. All right. All right, so now that we looked at the different detection method and basically had some understanding, we have some understanding now of how, you know, the diversity and why is it called as well. And so why do we study exoplanets, atmospheres, and how do we do it? Let me first show you a little video of the International Space Station from observation of the Earth from the International Space Station. And you see here, there is the atmosphere is actually really thin. Like it's pretty much 100 kilometers, a layer of 100 kilometers, and it's extremely, extremely thin compared to the size of the Earth. And it's, you know, if you were to study the Earth atmosphere from a very, very distant place, you would quite struggle. And that's what we're trying to do with exoplanet atmospheres. There's not much point, but it always blows my mind to see the auroras and how, you know, the auroras are actually a result from solar flares. So basically, the solar wind basically goes into space, and then it reaches the Earth atmosphere, where there is a magnetic field around it that protects us, because the solar flares are actually very harmful for us. And always blows my mind to see that. All right, remember when I mentioned the transit method? I said we look at basically when the planet is going in front of the star, and then we look at the brightness. And if we look at that at different wavelengths, we then can detect we basically can have a transit depth at different wavelength, and we can get a spectrum out of it. And with the by looking at different wavelength, we look at different depths of the atmosphere. So here the green one is the inner part, purple is middle part, and yellow is the outer part. And you see they have different transits, what we call the transit depth in the solar brightness. And from that, then you can acquire a spectra, and from the spectra you can do some analysis. Yeah, here is just an example of, I think, was it Venus transiting, or yeah, probably Venus transiting the star. And here's and you see here how, well, we don't really see it very well in this picture, but how the planets going in front of it, or maybe it was Mercury. Sorry, I don't remember what I put. But how by having the planet going in front of it, we can study the Earth's atmosphere. Oh yeah, so here is a spectra. All right, so now what is the point actually of studying atmospheres? Well, the first indication that we can have in exoplanet atmospheres is how did they form, because the atmosphere actually will carry some information that is that we can see that will give indication on the formation processes. And then the other thing is the impacts. If there's comet impacts, we can see it in the atmosphere. Then we can look at cloud and different structures and a lot of really cool things. And the atmosphere also indicates on stellar radiations. And the next thing is we can look at if there is any kind of atmospheric escape. And remember when I mentioned the hot Jupiter planets, which are Jupiter-like planets and are really, really cool because they're really huge and really close to their star. Well, it happens that these planets actually they are losing their atmosphere because they're so close to their star, and there is solar flares and like winds and stuff, and so they're basically losing some of their atmosphere, and we call that atmospheric escape. And then from the atmosphere, we can study if there is any volcanic activities, and that's how we can detect ocean world, lava world, sorry. And then eventually we can detect if there is, you know, carbon dioxide or methane or water, things that would be indicating of the presence of life. All right, before I go to the scientific questions, I see we have started an hour ago. I just want to check with you if you want to take maybe a 5-minute break, if it's good for you, and how are you feeling right now?
I think a 5-minute break would do.
Okay. Okay,
Yeah,
great.
well, unless it's just my opinion.
No, I mean I feel that's a lot of information for you, and maybe you want to take a little water break, or I will happily take a bathroom break. And okay. Nice question. Yes, of course, there is actually a lot of very interesting impacts, and impacts that we actually don't fully understand, because...
No, maybe you can read the question louder because everybody didn't read it.
Okay, so the question is there any impact that an atmospheric escape has on the planet? And basically, yes, the planet is actually very sensitive, and in some ways is victim of its star. And depending on the stellar activity, the planet will have a heavy impact actually, and will completely have an impact on its dynamic. So when there is an atmospheric escape, it's a pretty, I want to say, like almost a violent event where some of its atmosphere like fades away, and so you have some molecules, like the lighter molecules, that will go away. And some of these molecules, sometimes, you know, they have a greenhouse effect. And so by removing these molecules, that changes the heat of the planet, or that changes, you know, the dynamic, like the climate, I want to say, within the planet. And so all of the molecules, just like on Earth, you know, we have carbon dioxide, that is very that we talk about because of climate change, and that has an impact on the Earth's atmosphere. And by changing the chemistry, changing the molecules of the atmosphere, by either adding some, or with here carbon dioxide, or removing some with atmospheric escape, that has a huge impact on the whole dynamic of the planet. For us, with carbon dioxide, that creates climate changes. And with some, you know, what we call disastrous natural events, and that makes the ice, that there is a global warming, and ice melting, and some other big things that actually totally impact the dynamic of the planet. Does that make you happy? Do you have any other question?
Yes, it does.
Great, I'm happy. Okay, let's take a maybe 4-minute break. I will come back at 44. I will go take a little drink and come back. Okay.
Great. Okay. See you. I'm staying here waiting for you to come back. So little break for everybody. Thank you.
How is everybody feeling?
Here I'm cold too.
Okay.
You guys are there? Still on break.
Okay, let's, I'm gonna send a little text. Let me know. I worked on this presentation last night until very late. And so yeah, I'm a little tired, but also very excited to be here.
Yeah. But you're doing great. This presentation, I mean, I think you can just use it for all the level and just adapt what you said, because all the image, all the picture and the video are very you know, we can understand really good, even we don't have any background on astronomy. So yeah, so far you did a great job.
Okay, thank you very much. Okay,
So Bob is there, Sia
amazing.
is there, and Roque is there. Okay. So they don't interact with the microphone, but they are really there.
Great, amazing. Okay.
Yeah, great. Thank you, guys.
Yeah,
So,
thank you very much.
Give you back the mic.
Yeah. All right, so now let's look at some key scientific questions with exoplanet science. I've mentioned how understanding planet formation is very key to understand the diversity and to eventually detect life. So the first question is, how do planets form and how do they evolve? And then, what is the chemistry diversity of exoplanets? Because what we see on Earth and in the solar system, it happens that it's actually very different on other planets. So we try to understand. Is there a text? Okay.
It's just me on the chat.
Yeah, I'm glad actually I can hear the sounds so that I don't miss when there is something coming up.
Okay.
So yeah, as I said, the chemistry diversity of the planets that we observe, it happens to be so different from what we see on Earth and what we see on the planets of the solar system. So big question is, what is the chemistry diversity of exoplanets? And then how does chemistry is correlated with other parameters? And one of you asked, how is the atmospheric escape has an impact on the planet? And well, the chemistry has a huge impact on many planets, on many parameters of the planets. And we don't actually fully understand what's going on. We don't fully understand how does the escape impact the planet, but we observe some effect. We do observe that there is some things, but we are still trying to figure that out. And that's actually a field where climate scientists are actually collaborating with exoplanet researchers, because we see things that we could possibly see happening on Earth and vice versa, and observing how Earth behave could be indicating of what we are actually observing in an exoplanet. So there is a lot of back and forth between different fields of science, between astrophysics and exoplanets and Earth and climates and atmospheres and oceans, and all of it is just like, it's all one big thing, and everything is interconnected. And so we try to understand what is this interconnectedness, how is this whole, chemistry, atmosphere, planet, ecosystem behaving, and how are things correlated to each other. And then the next question is, do small planets maintain their atmospheres? And when, for example, in our solar system, we have Mercury, that is the closest planet to the sun, and it doesn't have any atmosphere. And in some cases, we actually try to underwood how does the size of the planet impact the type of of atmospheres that it has? Because would the gravity be sufficient enough to then keep gases of the atmosphere in it? And so for that, we need to study the atmospheres of a very wide number of planets. And this is why we developed the instrumentation. And this is why also we have the James Webb Space Telescope that is already revolutionizing our understanding of exoplanet atmospheres by studying a wider number of them. But it takes time, you know, it takes a lot of effort, it takes a lot of people, and there is a lot of work to be done, and actually a lot of citizen science projects. Actually, I would like to take some point at a moment, maybe at the end, to discuss citizen science. I will try to remember that. And here we'll describe I'm just mentioning the aerial space mission, which will be launched in 2029. The aerial space mission is a collaboration between the European Space Agency, ESA, and NASA. And the main point of this mission is to study the atmospheres of exoplanets and possibly to detect life. And so then I will dive into what are ocean worlds or water worlds, which to me are very interesting and fascinating because they could be places where life would be very abundant. So just to give an indication of Earth, there is a lot of water on Earth and lots of big oceans, but it's actually not that much compared to the whole amount of basically rocks that there is on the planet. And here is an actual two-size indication of how much water there is. There is only 0.1% of water in the whole mass of the Earth. And for ocean world, there is just 10 times more. So there is about 1% of water. And so that's and for so there is an example of a TRAPPIST planet, we call that. It's a system that has 7 rocky planets, and in one of them there is 50 times more water than the Earth does in terms of proportion. So it's a huge amount of water, and so we try to understand, like, how is that even possible to have so much water, and where is this water coming from? How does that have an impact on, you know, possible bioactivity in there? How is life also intrinsically, how is it linked with life? And so here's an artist illustration of this TRAPPIST-1F system. Actually, the TRAPPIST system was discovered by a Belgian team a few years ago. Like,
really?
Yeah.
In Belgium.
Yeah, actually TRAPPIST because of the beer, the Belgian beer.
Yeah. We love beer here.
Yeah. I'm curious if when, I don't remember who mentioned that there was at least one Earth-like planet that was detected. Maybe it was about this one. I don't know if you remember. Anyway, that's a very famous.
Most I'll say that.
Okay. Yeah, it's a very famous one, and it's like always happening in the news. There is another paper that came out like 2 weeks ago, like a research paper of studies from James Webb observing the planet TRAPPIST-1b. So it's a really cool system with 3 planets in the habitable zone. So what we call habitable zone is not too far and not too close, so that there can be liquid water on the surface. Oh yeah, here it is. Sorry, it's really just the right distance from the star to have liquid water on the surface. And here, for our solar system, you have Earth and Mars that are on the habitable zone. So, well, obviously on Earth we have liquid water, and it's what we call it the Goldilocks zone, because it's where life could emerge. And basically the place of this habitable zone changes with respect to the type of star and the age of the star. And so eventually Earth will not be anymore in the habitable zone, and basically it will move further away. And so that's why also people are trying to see how we could move eventually to Mars in a very distant future. I'm pretty pessimistic about that, but that's another debate. All right. So then where does the water come from? And water is H2O, two atoms of hydrogen and one atom of oxygen. And so hydrogen is actually the first atom that was created in the Big Bang. So in the Big Bang, you have at first just light, and light then becomes matter. It first becomes hydrogen. So hydrogen is by far the most common atom in the universe. And then there's oxygen that is created in the core of stars that are more massive than the sun. So the first generation of stars were actually really massive and created big heavy elements like oxygen. And for a couple of reasons, basically H2O, water, is the most common molecule in space. Just like it happens to just like come together very easily and very well. There are some atoms that just like match more than others, but like hydrogen and oxygen, they just get together super easily, and it became the most common molecule in space. And that's why it's so abundant everywhere. It's abundant on Earth. It's abundant on other planets. It's the origin of our oceans. Actually are in the stars. And actually, I mean, that's also true for all of us. Like, we are made of water, and our origin from the stars, like, we are literally the result of 13.8 billion years of evolution and the result of the light of the Big Bang. Here's an example of the Orion Nebula, which is in the Orion constellation. And just something that blows my mind every time is that it's so vast, it's so big, and so every point here is so a nebula. I should describe it first. It's like a big cloud of gas. It's like a maternity of stars, and sometimes the gas just like gets so dense that it creates it creates stars. And so the Orion Nebula is so vast that it creates enough water every day to fill Earth's ocean 60 times. So it's like a huge amount of water. And water, along with other molecules, becomes raw material for the formation of new planetary systems. And this is how we have so much just water worlds, ocean worlds. And so here's an image of just an example of how many ocean worlds do we have. So let's say we have 52 exoplanets. They're all low mass exoplanets, and a quarter of them would be ocean worlds, and an eighth of them would be covered by ice. So actually, water worlds are actually just very common. Ocean worlds are very common. And we have even examples in our solar system with the moons of Saturn and Jupiter. And here is the moon of this is an actual real image of Europa, a moon of Jupiter. It's an ocean world, meaning there is basically an ice cap, and underneath there is huge oceans. And here is Enceladus, moon of Saturn. And same, we have a huge, thick ice cap, but underneath we know there is oceans, liquid oceans, and we have. So here is also a real image, and we have actually flares of water coming, and we see there is methane that is like a molecule here, and so that could be indicating of possible life that would be present underneath. But yeah, there is actually some space missions that are focused on that aspect. And well, here is well, here you see like how thick actually the ocean world is, and just some images of things that we observe and what we have. This is more an artist impression. All right. So how is it relevant for our understanding?
I have a question. How do you know about all the colors? Because we can really see this color, or it's like it's coming from our imagination and the artistic view.
So, like for Jupiter, for example,
yeah, and all the gas, and we are sure that they have this color.
So yes, actually, so if you Google the Juno mission, actually, let me show you. It's like amazing colors. Can you see that?
Yeah, it's incredible.
This is actual real images. Can you believe that?
Really? This is not an artistic view of something.
No, it's for real.
Whoa.
This is actually for real. This is why I love astronomy as well. It's just like art is everywhere.
This is better than an artistic view, actually.
No, it's not.
No, this is better.
It is better. It is better. It is better. Look at that. I'm just mind blown because, you know, there's just like, that was my phone background for some time. And it's mind blowing how, you know, for me, when it actually, anytime I put my, you know, milk into my tea or my coffee, that's kind of how it looks. And so it just blows my mind to see how, you know, atmosphere is something, you know, that is dense and thick and things move together and there is storms, because all of that is storms actually. And so you have different molecules that behave differently and have different temperatures, and it's crazy.
Sure. And you have a question about that in the chat.
Okay. Yes, exactly. That's different chemicals. So basically, different molecules will emit light at different wavelengths, and that's what makes it different colors. And just every molecule reacts differently with different wavelengths, and that's what makes it so special. And so that's for Jupiter, but for Saturn, and there is the Cassini Saturn photos, and it's also really, really cool. So there is, I'm looking at, so that's an actual image of Enceladus. I'm looking at, look at that. Isn't it crazy? It's less impressive here, but it's still really cool. Have you seen this image before? Do you guys see? Damn, you know, actually, let me do that. So you see this point here? Can you see that? I don't know if you can see my screen. Yeah, here it's actually Earth. And so it shows really how tiny Earth is, and how that has an impact on you know, how we see the world. All right. How are ocean worlds interesting for our understanding of life? Well, on Earth, we know that life actually appeared from a mix of heat, energy, lights, and water. And so that comes from what we call thermal vents. You have the core of the planet that is very heat, that is basically creating a lot of heat. And so then you have what we call thermal vents. I don't know if you're familiar with this, but things that just emit heat. And so that's what makes also dynamics of the oceans. And here is an example of thermal vents in our ocean. And you see it's just like crazy colors, and where there is just crazy molecules coming from the core of our planet, not the core, but like from inside the planet, and there's just heat coming, then molecules that, or even sometimes dust and some other things that get emitted or just get freed through thermal vents. And because that brings some minerals and a lot of, actually that brings also a lot of nutrients for life. And that's actually very important for the life ecosystem of the ocean. And so, yeah, the energy source is now then chemical, especially in the depth of the ocean, is chemical and not sunlight. And life on Earth has originated from hydrothermal vents. All right, so here's basically how an example of how you have the rocky core here, and then you have basically hydrothermal activity where you have the magma chambers, where you have lava happening, and you have just a lot of motion that is happening. And then you have the first layer of the oceans that receives chemical energy from the hydrothermal activity, from the hydrothermal vents. And then you have the upper layer of the planet, in that case for Europa or Enceladus. And so you have this ice shell that has also water, and basically there is a continuous motion back and forth between the thermal vents and the water world, the ocean liquid water, and then the ice cap. And there is an exchange of matter and energy. And then at times you have a plume, so basically a place where there is a little crack in the ice shell, and that freeze, freeze in terms of like freeing some some water. And so then when you have some radiations, you also have an increase of temperature and basically an incoming amount of energy that also contributes to the whole ecosystem. And so then the big question is like how you see like some question marks here and maybe some bacteria. And would it be a place where there would be life? I mean, you can imagine some bacteria, or you can imagine also maybe some kind of like fancy dolphin that would be just like having their best life swimming in this ocean world. And so then the Fermi paradox, where is everybody? And the possibility is that the reason for the great silence is that there's just too many planets out there that are just too watery as well. And in some case, we could believe that would be very suitable for life, and in some other case, that life maybe needs some other things. Okay, here's a few examples of some ocean worlds. Maybe you've heard about the Kepler mission. It was a very successful mission that discovered the most exoplanets with transit, with the transit method. And here's a few of them that are, some of them we call that super Earth, that are between 1 to 8 times the mass of the Earth. And they just have a huge amount of water. Here's the example of Kepler 22b. It's 6 times the mass of the Earth, and its temperature, surface temperature, is 22 Celsius. So it's a very good target for possibly understanding if there is, life on it. And so there is something that is called the Earth Similarity Index. So basically, how close we are, how similar are we to Earth? So it's pretty high. Is it standard primary habitability, the middle? And so it's a very good target for understanding habitability. It's very far away. It's almost 600 light years away. Anyways, that's a really interesting target. And if ever you're interested, there is also really good documentaries on that I'm happy to share with you. And then the question then becomes, do planets lose their oceans over time? And what is it that we can observe on the evolution on other exoplanets that could also be indicative of what happened on Earth? And maybe you know that, for example, on Venus, so Venus actually used to be habitable, used to be suitable for life. But there was what we call a runaway greenhouse effect that boiled up all the oceans, which then escaped into space due to solar winds. And so when one of you asks for how does the escape impacts the planets, that's one of them. In some cases, like on Venus, the atmospheric escapes led to the oceans to totally boil up, and now Venus is completely toxic. It's like super hot. It's like continuous weather, warm, hot storms. And it's now that this is these greenhouse effects that keep Venus to be very, very hot. And there was what happened with this atmospheric escape is that there was a huge increase of carbon dioxide, CO2, that really increased the greenhouse effect. So that's something that could happen to our planets if we're not super careful with how we release carbon dioxide, and that's why climate change is, such an important thing. And astronomers are, hey, this is how bad we could turn with Venus. All right. So how do we find alien life on these exoplanets? And well, we cannot really... Oh my God, so loud. Yeah, I don't know if you can, I don't know if I can stop the sound. Okay. I really love this GIF because this is what if NASA had the same budget that the US military, and who knows, maybe we could travel there. Maybe some people would develop some fancy traveling things that would have us just move there. So the first actually, let me show you. The first image is how we got on the moon, and then on Mars, and then on other planets and ocean worlds, and maybe there is aliens. And so that's, I find it like just super funny to, so the US military budget is like crazy huge. And well, I'm one of those who love to criticize America for how stupid they are with, well, I shouldn't say that, with just how they use their money that could be used for science and humanity. And so then we can look at the atmospheres instead of, before moving there, because we cannot, we can look at the atmospheres, and the atmosphere is key to understand what's at the surface. And so we can, by looking at the atmosphere, we can find, for example, on Earth, we have 20% of oxygen on our atmosphere, and all of it is due to bioactivity, to life activity. And then we can look at water vapor, and if there's cloud, and if there's cloud, then there's climate, and if there is climate, then there is dynamics that is necessary for life. And then when there is bushfires and other things, there is an emission of carbon dioxide. And then we can look at other molecules that formed by intelligent life. And so here the main point that I'm saying is that just looking at what single molecule is not enough to say whether there is life or not. We need to look at very wide variety of molecules. Well, when there is a disequilibrium of molecule, like for example, when there is an excess of ozone or an excess of methane, that could be an indication that there could be a bioactivity, in a nutshell. And things are always more complex than expected, and it's not because you find these molecules, then you can say for sure there is life. Our only data point actually is Earth, and so we see that there's 20% of oxygen. We see that there is methane. We see that there is a lot of things that is necessary for life to happen and to flourish. But does it mean this is what we need on another planet? We cannot really extrapolate that way, and so we're in some ways limited by our own biases, and it's really hard to to fully understand what could actually happen. That's the whole point of what we call astrobiology, that looks at how could life evolve in different environments. All right. I'm finishing with this quote of Carl Sagan. Maybe some of you know of him. He is a very, very inspiring astrophysicist, or he was because he passed away, who wrote a few books and who played a huge role in the search for extraterrestrial life. And if ever you, there is a movie that is called Contact, that it's about connecting with alien civilization, which is really cool. And he says the universe is a pretty big place. And so if it is just us, it seems like an awful waste of space. All right. And thank you very much for your attention. Yeah.
Thank you very much, Nour. Is it Nour?
Yeah.
Oh, yeah, I'm sorry. I have a question that if I am an undergrad, right, in a physics major, and some of my colleagues here are undergrads in engineering. So if I were, or we were to be interested in astronomy, where would we start?
If you want to do an astronomy, where do you start? Well, I'm very glad you asked. So there is good ways to start is citizen science projects. And if you are serious about doing astronomy, I can put you in touch with many people that could help you. So citizen science, have you heard of what is citizen science?
No, I have not heard about that.
Citizen science is great because did you actually know that you can collaborate with NASA right now from where you are? And citizen science is basically how every single person can contribute to doing science with, you don't need to do 10 years of studies that I just did. I mean, if you want to be an astrophysicist, you will have to do that. But any student, any person can actually contribute to doing astronomy. And so your question was how to continue on studying astronomy, or how to sorry, you cut off at some point, so I'm not sure entirely.
Oh, basically where to start, where to start
to study astronomy. To me, I think citizen science project is a really, really good one, and connecting with astrophysicists, actually, let me, for example, send you a link to the Panoptes project, which is a typical example of a citizen science project. And there is also the Zoo Universe. And then there is, I don't know if you're familiar with Coursera. It's like online. Is it Coursera?
Yeah, we're familiar with that one.
Yeah, okay. So there is many ways where you can start by doing some astronomy. If you want to learn about astronomy, there is some really great resources online of courses on astronomy. And then, so citizen science, I think, is a really great way to start, because you learn on, on your astronomy topic, but at the same time, you collaborate with people to actually do science, to do astronomy. And there is a bunch of citizen science projects that exist. And if ever you're interested, please reach out, send me an email, and that would be another hour conversation on how you could start on citizen science projects, as in like how you could be doing some science and collaborate with some researchers and have some, you know, possibly even opportunities of publishing a research paper.
Okay, okay. Thank you so much. It's because there's a part in the video where you showed like a telescope and that you were working on it, and I was like, I want to like know how to build a telescope.
Yeah.
So, yeah.
Okay. So there is courses on, so for me, I did an engineering school in optics and photonics. You don't necessarily need to do that. I think the best, if you have the opportunity to do some internships, I can put you in contact with some people that would be, I'm sure, very happy to give you internships. Internships are a great way to learn. Doing some studies in optics and photonics, or optics is great because optics is basically the science of light. And when you study astronomy, you're pretty much playing with light and studying light. And you need to have some kind of understanding of the technical aspect behind it. You don't necessarily need it. If you also stick with just the pure science part of it, it's also an option. There's just so many options. And if you also stick with just mathematics, there is, I like to say something that every path leads to astronomy. You can do whatever you feel like you are interested in. And if astronomy is your goal, there will always be a way to make it, to make your way. Do you know? Sorry, go ahead.
Oh, I was saying that are the internships available for everyone? Because most of them, I realized that they need like postgraduate qualifications. They're like, if you have like an undergrad a basic degree, then you need to get a higher qualification.
Actually, that's not true. I mean, for like the official ones, yes, but you can always reach out to a scientist and say, and this is what I did for all of my internship. I said, I looked at someone online and I looked at who was doing something that I was interested in. And I found the email of that person. I said, hey, like, I'm a student, I'm first year, I love what you're doing, I don't understand anything, but can we chat? Do you have something for me? Can we do something? And in some cases, people didn't answer me. Some cases, I was just so interested, I just kept harassing them. I said, hey, you didn't answer, but I'm still very interested. And eventually, you know, like people are actually, they want to have some people that are willing to just learn, you know. And if you just reach out to some astronomers or even any kind of person that you're interested in, sometimes do not just stay with what is official, but try to see people directly, and very often they will be willing to have somebody that doesn't necessarily have the qualification, because we've all been there, you know. We've all been to a point where we didn't have any qualification, we didn't know who to ask, we were afraid of not being enough, not having good grades enough, and that can be stressful, but it's actually not even that important. And so what really just matters is for you to find someone that you're interested in, find a couple of people and just email them. Just try it out, even if they are at the other end of the world. Sometimes they will even have funding for you to travel.
Oh, okay. Thank you so much.
And let me send you again my email address. And if ever you want to discuss, or if you want to discuss more, what is it that you're interested in? What is it that you're looking for? Maybe I can help.
Okay, thank you.
Of course, thank you. Do you guys have some other questions, maybe? Mosa, did you like the presentation? Was it clear for you?
Yes, I like the presentation. I've had this love of, I call it the solar system because I've only just learned of the term astronomy recently. So my dad used to like take me out of the house during the night, and then he would show me the planets and the stars, and he would say, "Oh, this forms when this happened," and then he would show me cool things like it's a halo, it's all those nice things. So it's always been intriguing to me, the basis of the universe, because he introduced it to me at that age.
That's amazing. That's really cool. Is it something, would you like to continue in astronomy?
Yes, because just to understand, the aspects that are like why, and there's this thing that I just learned about called dark matter, and you just said that dark matter contributes a lot into the universe, and it's very intriguing.
Yeah, it is.
Yeah.
Send me an email. We should talk.
Okay, I will send an email. Thank you.
Okay. Because I would love to tell you more about Citizen Science Project and maybe find something that you will find interesting and that will help you to concretely move on with doing some, there's without any commitment, even just doing some small things that will maybe inspire you.
Okay, I will definitely send that email.
Yeah.
Thank you
Great.
so much.
Well, thank you to all of you. It was really great presenting for you this morning. And I'm glad you got out of bed to listen to me. Thank you.
Thank you so much.
Thank you. Thank you very much. I don't know at what time you have your other class. I think
it's at 11.
Dora, do you have
We have a class at 11.
Oh, at 11? Okay, so you should take some time to relax and breathe so then the next class is nice.
Yes. Thank you.
Okay. Thank you so much to all of you. Thank you. All right. Have a wonderful day. All right. Take care. See you at some point.
Yeah.
Oh, hello. Is it you or Dora who recorded?
Yeah, it's Dora. That's why I'm waiting for her.
Oh, okay.
Yeah,
Okay.
I'll tell her right now.
Okay, thank you.
Would you want to do something with the recording?
Yes, we are going to send it into the group chat.
All
the
right.
one
Okay.
for
Good.
physics students. Yes. Thank you.
Thank you. That's cool. And if you have some feedback, let me know. If people would what they liked and what they would have liked to see any difference. Yeah.
And also the question.
Yes, any of those questions, of course. Keep my email address to send them.
Okay. Thank you.
Of course.
Thank you so much, Nour.
My pleasure.
for taking your time. And yes, I hope you enjoy it as well.
Yeah, I had a great time. Thank you.
Yeah. Merci, je te remercie vraiment. J'avoue que sur la fin, j'ai dû passer sur un autre appel, mais sinon, j'étais là quasi tout le temps.
Pas de souci, je n'hésite pas si tu as des retours et Et Mossa, elle disait qu'elle aimerait bien avoir le recording pour le partager aux autres étudiants.
Ok, ça va, bah, c'est super.
Voilà, merci en tout cas.
Bah, merci cool. À toi. Merci à toi. Là, ils ont une pause et figure-toi qu'ils enchaînent dans une demi-heure. Ils ont un autre cours sur la physique des particules.
Ouais, c'est génial ce qu'elle disait, Mossa. C'est ce que je disais aussi, ouais, c'est sympa.
Voilà, voilà. Ah mince, j'ai même pas ma caméra. Voilà. Je te parle de tout à l'heure. Ok, ça va. Mais écoute, merci beaucoup. Et nous, on se tient au courant quoi qu'il arrive. Et quoi qu'il, de toute façon, on se voit à Kinshasa.
On se voit dans une semaine, ouais.
Ouais, ça marche.
Allez.
Merci beaucoup, Nour. Salut.
Bien. Salut.
Ciao. Alors, voilà.